Greetings all, and thank you for taking the time to tune into yet another iteration of the Federal Laboratory Consortium's Lab Showcase at the National Institute of Standards and Technology. While we have already introduced you to our world-renowned laboratories and some of the manufacturing programs, today we're going to dive a little deeper into the weeds to showcase one of NIST's cutting-edge technologies. And I have to say, as a recovering nanotechnology nerd now in policy work, I'm pretty dang excited for this session. But before we jump into the important stuff like the low-cost, large-scale, non-cryogenic hydrogen storage technology we're about to learn about, allow me to shamelessly plug myself in my office. I'm John Bittman, an interagency policy specialist in the Technology Partnerships Office at NIST. Our office serves NIST researchers and other customers by structuring the collaborative relationships with businesses of all sizes in every industry. We also serve the interagency technology transfer community through our various consensus building, forum establishing, and/or best practice sharing efforts. And through that interagency role, I serve as the host agency representative to the FLC. As you may or may not be aware, NIST serves as the host agency to the FLC, which means we provide administrative and other support services to the consortium as mandated by Congress through legislation. So one ground rule before we start, if you have any questions for the presenter, please submit them through the Q&A box and we will try to get through as many as possible following the end of our rather brief presentation. But so now that we're all squared away, I'm happy to introduce our featured presenter who will need no such squaring away, Dr. Hayden Evans, a research chemist in the NIST Center for Neutron Research. So without any further ado, let me go ahead and turn the floor over to Dr. Evans. Welcome.
Hello. Hello, everybody. Thank you so much for that kind introduction, John. As was said, my name is Hayden. I'm a research chemist at the NIST Center for Neutron Research on the NIST campus in Gaithersburg, Maryland. This is a very pretty picture of the NIST Center for Neutron Research in springtime bloom, as we're going through currently right now. But the facility, for those of you who don't know, it's a nuclear reactor, right, where we generate neutrons to study materials. We work alongside academic, government, industrial partners who are interested in studying their materials or their substances using neutrons. And so if you have any general interest or are neutron curious as to how, when we are operating, how we could assist you with any kind of work, please contact myself or contact Ron Jones at the NIST Center for Neutron Research. So today we're going to be talking about some of the work I've been engaging in over the past couple of years that we've finally sort of put out into the world. It's regarding a low-cost adsorbent for large-scale non-cryogenic hydrogen storage. But to be able to sort of explain the material and how it fits into the larger landscape, I will cover both sort of the hydrogen storage economy, how it's sort of picking up, the material itself, which is aluminum formate, ALF, how it fits into a larger landscape of renewable energy technology, and how that will feed into its more than likely growing scalability options into the future. So that's what this slide says, right? So motivation and significance, and then we'll talk about ALF, which is a emerging industrial adsorbent based on the work and myself and collaborators have been doing over the past couple of years. So, as we may all appreciate, the world is shifting away from fossil fuels, right? And along that comes the development of new technologies, many that have been worked on for the past couple decades and some that are only now emerging, right? But as we move away from fossil fuels, we're not going to completely replace them with just one of these technologies, right? We're going to build this sort of patchwork arrangement of all these different things. So geothermal, wind, solar, nuclear, hydrogen, all of these technologies have a place and an application where they're going to be best suited. And so we need to figure out where that is and then leverage their advantages where we can. In terms of hydrogen storage, hydrogen energy applications, This is only going to continue to grow, and as all of us who probably know on the call, there's been a massive injection from this administration as well as our legislative branch in the form of $7 billion worth of funding towards the development of clean hydrogen hubs, which is going to obviously, be a large energy investment, developing good paying jobs and infrastructure, as well as improving the United States energy security, right? So there's a lot of economic potential in the development of this, hydrogen economy, as well as for the people on the call from the government, right? This is a national security interest as we diversify and make redundant areas of our, energy tapestry, if you will. Currently, how much hydrogen exists globally, right? How much are we actually making? And so what I'm going to do now in the next couple of slides is sort of show where we are and how the DOE, from their report from 2020 for enabling a low carbon economy, what they sort of predict, right? So the current landscape, this is from their picture here. You can see that, on the left-hand side, we're generating most of our hydrogen from oil equivalents, right? So natural gas, coal, oil. And this hydrogen is being used primarily in refining, ammonia production, methanol, as well as sort of mixed gases and the development of other things, right? So pretty much the chemical industry, not too much for energy demands. In terms of what these numbers actually mean, right? So it's about 100 million tons of hydrogen is being, used and produced globally. 10 million tons of hydrogen is equal to 330 terawatt hours, give or take, right? So we can think of this in terms of actual energy. An annual electricity bill in the United Kingdom is about 300 terawatt hours, right? So you can think about 10 of those, 10 United Kingdoms worth of electricity is how much hydrogen we sort of have on hand at the moment. In 2050, the DOE predicts that that kind of chemical industry feedstock dependence will still be there, if not grown. But then there's also going to be this massive expansion, 3, 4, 5 times the amount, whether it be in power generation, transport, the development of transport energy for using hydrogen, industrial energy, heat and power, right? So there's absolutely massive growth potential in this field, right? And that's going to be dependent on our development of a supply chain and technologies that can support this kind of expansion, right? So this is obviously hypothesized, predicted based on what we would hope to reach, but it's very much dependent on the technologies that we use and the processes that we get to get this off the ground. And if you read Forbes, this came out yesterday, so I thought it was worth probably talking about. So the green hydrogen becoming new oil, right? So there's $1 billion today, sort of a global market for green hydrogens, can be 30 billion in 2030. But obviously this lack of transportation and storage infrastructure is the barrier to growth, which is why we're talking about our technology today. So aluminum formate is an adsorbent material, right? And so it's worth discussing what these are, maybe more generally, and then sort of hone in on why they're useful to the future hydrogen economy, right? So adsorbents are incredibly important solid state materials. They have massive implications in the chemical industry, but obviously for hydrogen as we go forward, right? So you may have encountered activated carbon. This is used in water filters. It's used in our nuclear reactor, right, to capture nuclear effluents. Zeolites, these are used in many different applications, whether it be from kitty litter to the multi-billion-dollar sort of cracking catalyst industry for fossil fuels, right? So there's both natural and man-made zeolites. These are a large class of compounds, but they are adsorbents, right? And then you have what are known as MOFs. You may have seen this acronym come up. It means Metal Organic Framework. These are the up and comer adsorbents, right? And they're chemist playthings, if you will, right? So they're composed of metals and organic moieties that we put together to construct our porous frameworks that we can use for adsorption or catalysis or anything along the like, right? So these adsorbents, they have many different applications, whether it be separations of storage or catalysis, but this is just some, article from Nature from 2016 saying, in the name of separations, right, these kinds of materials are very important and they have large, wide-reaching implications for the future, right? Whether it be rare earth metal acquisition from ores to uranium from seawater to greenhouse gas capture from dilute emissions, right? And just in general, sort of chemical separations, which are very much dependent on adsorbents, and easier ways to do this account for 10 to 15% of the annual US energy use, right? So making better adsorbents not only improves our general chemical industry, but just our general energy use, which relates back to what we're talking about today. So porous adsorbents, right, or just adsorbent, adsorbents we're talking about there, are vital for hydrogen storage, right? So they enable storage densities. Sorry, here I can't quite see this. They enable, higher storage densities of hydrogen at lower pressures and higher temperatures, right, than just compressing hydrogen. So the reason why we'd even use an adsorbent, I mean, simply put, is that it's lower cost, right? It's less intensive to be able to enable this technology. And this is because hydrogen is very light, right? It's the lightest element, and it's not very energy dense, right? So to actually achieve the kind of energy densities you need for transport or general energy storage, right? It means that if you're going to just compress the gas, you need very high pressures, so 350, 70 bar, as well as low temperatures, right? So beneath like 77 Kelvin. And you can imagine this is quite intensive. When you use something like an adsorbent, which given their very, very high surface areas and their high, favorable atomic arrangements, based on the chemistry you make these things out of if you design them in the right way, this can promote the hydrogen storage at higher temperatures and lower pressures, right? So lower cost, more efficient, less intensive. It's the whole reason why such materials are sought. But if you don't have sort of an idea of like what they are still, right? They're like sponges. They're materials that have very high surface area, like this, like this sponge, right? And there's some of these adsorbents that have been developed, not necessarily for hydrogen storage, but other applications that have just really amazing properties, right? They might have surface areas like in a teaspoon of this type of material that if you fold it out and you made it a flat surface is equivalent to a soccer field, right? And that's kind of mind-boggling to think about these materials we can design that have these kinds of surface areas. The fundamental, sort of phenomenon that you're engaging here to have the hydrogen storage in some of these absorbents is physisorption. I draw this contrast because there are other materials like hydride materials, which are engaging in sort of chemisorption. These have utility in certain types of hydrogen storage application, but just to draw the sort of contrast here, adsorbents that are engaging in physisorption are a little bit more energy efficient because there's not actually any breaking of the bonds of the hydrogen, right? So when you use something like a hydride material, you actually break the hydrogen apart and you fix it in a different way, whereas in using an adsorbent, that hydrogen molecule stays intact and just floats into the porous network. And so there's less energy loss gained in that kind of process. Okay, so now we're going to move into talking about the actual adsorbent, which our work covers. This is aluminum formate. We call it ALF. So I'll talk about the crystal structure, and I'll also talk about first its utility for what we studied first, which was CO2 capture. But I want you to bear with me here because it's important to establish how this material has wide-ranging utility, because the scalability and the cost of this material is very dependent on what we believe it can be used for. Okay. So this is aluminum formate. We first reported this manuscript in 2022, but the work on this aspect of aluminum formate started before that with our collaborators in Singapore. So this is an earth-abundant, scalable, and highly selective material for CO2 capture, or at least that's how we sort of published it, right? And that's pretty remarkable. On the left-hand side here is the chemist's depiction, right? The crystal structure of what aluminum formate, or ALF, looks like. And so for those of you who are not well versed in thinking about crystal structures, this is what this picture is saying. So these little octahedra here, they're describing where the aluminum sits, the kind of local environment that is. So the aluminum is 6 coordinate, so it's an octahedra, 6 bonds. These bonds are to oxygen atoms. These oxygen atoms are contained within this formate, right? So this organic moiety, which is the conjugate base of formic acid. So without those sort of chemistry terms, what am I actually saying, right? Well, to make ALF, you combine aluminum hydroxide and formic acid to make this, as made aluminum formate, and then you have to heat treat it again, and then you make ALF, and that's the material we would use for CO2 capture or hydrogen storage. This material is remarkable in its simplicity, but also in its stability. It is air stable. Many metal organic frameworks are quite air sensitive. You can't breathe on them without them sort of falling apart. Aluminum formate can be boiled in nitric acid and it comes out just fine. It's really strong. But we also know it's pelletizable. And in fact, some of its CO2 capture properties get better once you actually put it under some pressure. That is also distinguishes itself from some of these other large pore adsorbents, which have quite large void spaces, and if you pelletize them or pressurize them, they kind of collapse. So these are two things that I believe are lend well to its industrial application in general, as we discuss these other things. So to add the context as we build up to the hydrogen storage here, aluminum formate, we first understood it to have the ability to absorb CO2 at elevated temperatures, right? So I'm showing these gas isotherms. This is what I'll show for the hydrogen storage, but this is just for CO2. So CO2 absorbed in terms of millimoles of CO2 per gram of material. For context, this 4 millimoles a gram of CO2, that's about 20% weight of CO2 per formula unit of ALF, right? So it can stuff itself full of CO2. But the thing is that it does it at higher temperatures, right? This is relevant because these higher temperatures is where you would want to do CO2 capture in a flue gas. Flue gas is made out of high humidity, some caustic, icky stuff, these SOx and NOx compounds, as well as nitrogen, right? It's about 15% CO2, 85% nitrogen. So what makes ALF useful for this kind of application is high temperature CO2 capture, and it ignores nitrogen simultaneously, right? So it has a very high selectivity. So that is really, really great. Its downside is that it doesn't deal too well with high humidities that you get out of a flue gas, because it's not a gentle capture event. There's a reason why we don't have very large scale CO2 capture to date, is because it's a very ugly event and you need a quite remarkable material. However, and this will make sense why I'm talking about this as we go into the hydrogen storage applications, right? ALF is a shelf stable, highly selective material for CO2 at these elevated temperatures, but most importantly, it's very low cost, right? So the predicted cost, if you go to the grand chemical sorcerer of Alibaba, right, is that when you make ALF, aluminum hydroxide is about $1 per kilogram, formic acid can be about $1 per kilogram. So our conservative number here is about $2 per kilogram to actually make this material from the raw materials themselves, right? Versus other leading CO2 adsorbents, that's about $20 to $100 per kilogram, right? So with this kind of low cost, we envision that aluminum formate could be used for this with a drying step, right? It's so low cost that there are other engineering solutions that in some materials may not be possible, but for this we think are, right? So here's the kicker, right? To solve the CO2 capture problem, you need a material that's both cheap, efficient, and scalable. A single coal plant could produce about 20,000 metric tons worth of CO2 per day, right? So you have to think, okay, we can capture all that CO2, but what do we eventually do with this, right? And that's because we believe that ALF is a keystone material to this CO2 capture cycle. And this is why its cost and its use in the future for many industrial applications, including hydrogen storage, is something that's quite promising. So if you imagine we're making our aluminum formate or ALF here with formic acid and aluminum hydroxide, which is a byproduct of aluminum processing, you make your ALF and then you can put this on the shelf. You can then recycle this ALF that you use to capture CO2, and then you can take that CO2 and combine this with something like solar hydrogen via electrolysis, which, for hydrogen storage, that might be one of the other ways that we make it. And then you make more of your formic acid, right? So you can see here that the CO2 capture cycle relates to the kind of feedstock you would have for aluminum formates. And you may also notice that formic acid is also quite relevant to the hydrogen storage industry, which I'll talk about now, right? So if we think that we've got tons and tons of formic acid sort of lying around, what do we do with it? If we turn into ALF, what can we use ALF for, right? And so this is where our technology sort of like started to take off a little bit, or what we thought about. All right, so this is covered in a non-provisional patent that was filed in 2024. It's titled this. The work that was done on this aspect of ELF to figure out the fundamental properties for hydrogen storage was done by myself, Tanner Yildirim, and Craig Brown at the end here. This is our scientific publication, which had context and other things added from our collaborators. And I mentioned some of those here in a second, right? So I'm by no means an expert on supply chains, but this is generally how I think aluminum formate, based on its fundamental properties, would fit in to this future hydrogen economy, right? So the fossil fuel economy, or I guess any kind of supply chain, looks like this, right? You produce your fossil fuels, you transport them, you store them somewhere, then you transport them again, you store them, and then you use them, right? The hydrogen economy would look somewhat similar, right? You'd have, if we're thinking about just straight, hydrogen, you would produce it, transport it, store it, store it again, and then use it. However, as we sort of talked about before, why we would even need an adsorbent, or why you need any of these other forms of hydrogen storage materials, is that pure hydrogen gas itself is finicky, right? It's very light, it has a tendency to be very difficult to store, right? You need these high pressures and low temperatures. If you're dealing with liquid hydrogen, right, there's another quirk, which is sort of the ortho to para transition. This can produce a boil-off event where you actually have a loss of your hydrogen that you're trying to store, right? So if you're dealing with like liquid hydrogen or liquid hydrogen, you'll have these loss mitigation steps that you would need to incorporate to this. And so that's probably why this is not likely going to be the way that we deal with sort of hydrogen, unless we make this big jumps in technology. And so they propose having hydrogen carriers, right? These are things like ammonia, methanol, formic acid, right? These kind of small molecules that you could more easily transport either as liquids, put onto trucks, tanks, move them around, and then break them down to release the hydrogen and feed them into the last stages of the step, right? And so we see ALF, or just adsorbents in general, fitting into these areas, right, based on its fundamental properties, loss mitigation, and sort of storage. But more generally, if we think about where these adsorbent materials could fit in, and I will say there are other solutions to this, right? There's plenty of other excellent technologies that are coming along, other forms of materials, other engineering processing techniques to be able to do some of these things. But obviously I'm kind of biased because I work on aluminum formate and adsorbents in general, right? But this is kind of the areas where the adsorbents fit in, right? You have your grid level storage, you have your boil off capture, and then you have an adsorbent or a material that you would use inside of like a vehicle, right? And each of these three areas here are challenging in their own right. So for like grid level storage, this large level storage, the goal of the adsorbent material that you would use was that it stores hydrogen better than compressed hydrogen alone, right? And by that I mean better, I mean lower cost and safer, right? Because we're not dealing, you preferably don't want to deal with 350 bar, 700 bar worth of pressure storage if you can get away with it. The advantage though is that you're not necessarily bound by space constraints, right? You have a little bit more space to work with. You can put it in the field, you can bury it underground, because it's the grid level storage, right? You're going to move it somewhere else. But if you want to do the large scale storage, you're not necessarily bound by volume or weight per se. For the boil off capture, this is relating to sort of the liquid hydrogen component of this. You want to be able to capture the hydrogen that's being kicked off at lower pressures. This is kind of where it's being off gassed, and then ideally sub 77 Kelvin, although depending on the kind of engineering, it could be slightly higher. I'm not the foremost expert on that part, but that's what I would envision. But it's important because there's like significant loss events. So if we're trying to limit the cost of how much this, this kind of economy or the supply chain would be, you want to make sure you don't lose hydrogen along the way. And then adsorbents could be used inside of vehicles, right? These are some of the more challenging kind of things to do, right? And the DOE envisions this kind of transport being possible for hydrogen. But you have to imagine the kind of adsorbent has to be able to absorb or store the amount of, or have the kind of energy density of hydrogen that is comparable to like a fossil fuel tank, right? And so that's very, very difficult. And some of these materials are quite expensive. They're also volume and weight constrained. So the ones that can do this are really remarkable. They're very, 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 very cool. Aluminum formate, just based on its chemistry, its crystal structure, its density, its cost, we see, and its fundamental hydrogen absorption properties sit here in our mind, in the grid level storage and the boil-off capture. And so this is the graph I will show, but I have others in other versions of these metrics if you're interested, because this part will be kind of brief here because, it stores hydrogen, but there's not many other ways to sort of say it, right? What you can see is that aluminum formate achieves hydrogen absorption at 120 Kelvin and then, up to about 233 Kelvin in my mind, where it starts to become closer to compressed hydrogen metrics, right? NIST defines cryogenic temperatures as 120 Kelvin and below. So non-cryogenic temperatures would be anything above that, right? You can see that even at 120 Kelvin though, that you get this very rapid absorption of hydrogen into aluminum formate at very low pressures, right? So we're going upwards towards 11 grams of hydrogen per kilogram of ALF, right? And this is an excess uptake. You can imagine though, the reason why this metric, maybe you've heard other numbers for the grams of hydrogen per kilogram of material that you're seeking out. But remember, aluminum formate is probably closer to $2 per kilogram, right? So, 11 grams of hydrogen per $2 per kilogram is sort of maybe the number you might want to think about. And depending on sort of the engineering and what is maybe useful, you might want to go to a slightly higher temperature. Maybe this is a better cost point in terms of the infrastructure needed to keep these kind of temperatures and pressures. But as I'll sort of show in the next couple of slides here, ALF shines at these moderate temperatures and these low pressures relative to the higher pressures, right? So if you think about just the fundamental comparison to the properties of if you compress hydrogen, you do a temperature pressure swing. So if you're doing 25 bar of stored hydrogen, and then you swing that temperature up to 296 Kelvin with 5 bar, these are the kind of volumetric storage metrics that you're getting for something a little bit different here relative to ALF, where you can see that if you vary the temperature and you go slightly lower down here, that even at 233 Kelvin, we're more effective than compressed hydrogen. And then 200 Kelvin, 160, 120 Kelvin, you can start to see the gains. And as I was sort of saying, you might think that you could go to higher pressures and maybe you can get a little bit more out. And yes, but also no. And that is, again, the plus and minus, just sort of how it is about aluminum formate. It's a very dense crystal structure, right? So it contrasts some of these larger pore adsorbents where you can push the pressure higher and higher and you can get more and more storage out of the material. But aluminum formate only has so much space, right? So it's very good at absorbing an X amount of hydrogen at these low pressures, but that's pretty much the gain. So this is why grid storage or boil-off capture kind of makes sense, opposed to that very high density that you would see inside of a car. And the point's proved that when you go to 100 bar and further. The last thing I'll sort of talk about is the metric here is that we had techno-economic analysis done by our friends, Dr. Hannah Brunig and Dr. Peng Peng at the Lawrence Berkeley National Lab, who are funded by the EERE and Highmark. And they added some beautiful context to what we already sort of suspected when we looked at aluminum formate or ALF for these properties, right? And what they show is that they ran it through their techno-economic sort of framework of analysis, right? When they're comparing sort of installed costs here. And what you can see at this 120 Kelvin range, the $2 per kilogram, we're already way cheaper, or at least middle of the estimated value or cost for compressed hydrogen at 350 bar at room temperature. And even if you push the cost of ALF to $10 per kilogram, we're still edging close to sort of the upper bound of the compressed hydrogen, but now at a fraction of the pressure, right? And so you can see in B here, if you compare 120 Kelvin of ALF storage capacity at 120 Kelvin, so 15 bar, versus that of compressed hydrogen 350 bar, you're hitting the kind of energy density. It's about 60–70%. In C, what we're showing here is that compared to nickel to metal-DO BDC, which is a metal organic framework that would be thought to maybe be used in like a car. That's the kind of high storage densities, those kind of adsorbents that you would need for that. What we're showing here is that it's one of the, based on our understanding of the material, it can hit that ideal pressure within that we would think would be safe for sort of large scale storage, and still keeping the installed costs between 1,000-ish, 2,000-ish dollars per kilogram. And then the last one here is just to add a little bit extra context, which is distinguishing ALF from other adsorbents in the field, which is to say that it doesn't work best at low temperatures and high pressures, or high temperatures and high pressures, but instead it is this intermediate zone, right? Low pressures, moderate temperatures. That's where aluminum formate sort of shines. And so the last thing I'll end here, sort of the conclusion, which is sort of summarizing the bit, is that it presents an opportunity for low cost, low pressure, moderate temperature hydrogen storage, right? ALF is currently, as far as we know from our techno-economic collaborators, the only MOF that's cost competitive with compressed hydrogen. It is air stable. It is a pelletizable material, which means that if you had to ship trucks of the stuff, it would be easy to deal with. It doesn't degrade unless it's being blasted with high humidity and high temperatures, but it works fine. It deals with high humidities at room temperature, as far as we understand. It works at a fraction of the pressure of compressed hydrogen to get the comparable storage densities, right? So 15 bar versus 350 bar. And given its potential and its position in a CO2 capture cycle, which would be rooted primarily in the upcycling to the creation of formic acid, the scalability of the material is envisioned to become cheaper with time, especially as the electrolysis and the development of making formic acid from CO2 and hydrogen straight becomes more efficient, right? And so our areas of how we could see this technology sort of applied, you can think of it for use in critical infrastructure backup, right? For hospitals, data centers, anything of national security importance. Generally, like a hydrogen fuel station storage, like a big tank underneath one of these hydrogen storage facility, or hydrogen delivery systems. Boil off capture, and then large scale storage. But I'm sure there are plenty of other ways that some of the people on the call could envision using this. But what's contained within the patent is the fundamental adsorption of hydrogen into ALF, and then the new form of matter, which is ALF full of hydrogen. And with that, this will be brief. I would be happy to take questions from anybody who's listening, but thank you so much for letting me speak.
Yeah, Hayden, that was a fascinating talk. I've got a lot of questions. You answered a lot of them as we went along the journey, but could you talk a little bit about the release mechanism?
Yeah. What would you like to know?
How's it happen? Is it easy and scalable as well?
Yeah, that's a good question. So this pressure temperature swing here is how we would kind of envision it. And then we're getting into sort of the engineering aspects of these things, right? So the process itself is something that we're thinking about. We're collaborating with people from Highmark and the DOE to think about some of these aspects here. But as you can sort of think about this isotherm graph here, just changing the temperature changes how how much hydrogen would be contained within the material. These are as a function of equilibrium, right? But at these temperatures above 120 Kelvin, the kinetics are quite quick, and so by just changing the pressure and temperature a little bit, you would see this change. So that's why we probably think about it like this.
Wow. And so along with other engineering challenges that will have to be overcome, what do you see as the immediate next steps required for this technology to make it into the marketplace? I know you've already talking with collaborators, but what kind of things are we going to see along the way?
That's a great question.
TBD, huh?
Fundamentally, I would probably say that it relates to that first question, right? The release mechanism, designing a process to make this efficient. And if it involves some sort of temperature component to it, you need to make sure that it's efficient. That would probably be, because after that, just it's really a wonderful material to work with because it absorbs hydrogen. And as far as we know, it's recyclable in the sense that it goes in, goes out. There's no chemical change in the material. It's a physisorbent. It's very durable. And so
And
figuring
not
out
very
that part.
hazardous, I assume.
No, no, I mean relative to relative to like other things that are potentially proposed for hydrogen storage, aluminum formate is as gentle of a material as you're probably going to encounter.
Hmm. Well, I think we might have already touched on this one. Oh, well, we have a question about what about other adsorbents regarding the grams per volume, nanographites or other nano compounds.
Yeah, is the general question of how it relates to that.
Yeah, how it relates, or how's it comparable to, or what?
I think, I mean, like, so this is the thing when it comes down to, because people, I think, were originally asking, so like, what's its weight percentage storage, right? Like, how much weight is stored with the hydrogen? It's about 1% or something like that. But I really, in terms of the cost of these things, and I don't know those numbers off the top of my head for the other comparable adsorbents, which is why I'm interested to see what people start to think about after this technology. But this, the the thing that I think is so significant about this is that one, the synthesis is quite simple. And so when it comes to scalability, that is something that aluminum formate has got in spades. And then the fact that it relates into this larger cycle of the precursors being not only waste products, but potentially related to something that, you know, the government is already sort of feeding into, which is the carbon capture subsidies. I see that this material has many things going for it, where some of these other nanocarbon materials or other kind of graphitic carbon materials may or may not have the same kind of advantages. But that again is just I don't know that as well. So I'm if somebody proved me wrong, I'd be okay with that.
Yeah, and I think you touched on this pretty much throughout the presentation because we've talked about the cost, the storage, everything. But we have a question that could you elaborate a little more on the distinguishing features of this low-cost adsorbent that makes it suitable for large-scale hydrogen storage?
I think that one of the things that lend well to this large scale hydrogen storage would be the general amicability of the material, right? Is an air stable material. Many adsorbents require that you treat them with gloves on, whether that be because they're slightly toxic or because if they are exposed to air, they may not be selective to just hydrogen alone. Aluminum formate is selective to hydrogen, or it can deal with being exposed to air. You can ship it on a truck and it's not going to require a lot of it's not a diva, if you will. It's because really what happens if you have this most sort of large scale storage event where something like the tank ruptures or something strange like that, is the material trashed if you have tons and tons and tons of the stuff that's storing hydrogen? As long as you don't produce another event where you're going to release all the hydrogen, the material itself is fine, right? So it is a very robust material, and it's very simple to make, and it's very scalable. I see those as being very attractive things for large scale storage, in my opinion.
Now, it sounds like it's going to see some developments over the next several years. So I don't believe we have any more questions in the Q&A box. So Dr. Evans, let me go ahead and thank you again for your contribution to today's presentation. And as our audience has seen, NIST has some real special technologies for partners to collaborate through licensing and or co-development. So I encourage all to visit the NIST and the FLC business websites for additional information on these specific technology partnership opportunities. So Hayden, thanks a ton for joining us today.
Thank you. Thank you for having me. Thank you for everyone for listening.
All right, everybody have a wonderful afternoon.